Hello, my name is Juan Gómez-Luna, and I'm a senior researcher in the Safari Research Group at ETH Zurich. I'm going to present our work understanding a modern processing in memory architecture, benchmarking and experimental characterization. Let's start this talk with a brief executive summary. In current computing systems, the data movement between the memory and storage units and the compute units is a major contributor to the execution time and the energy consumption. Processing in memory is a promising paradigm that can tackle this data movement bottleneck. Processing in memory essentially consists of placing compute capabilities near or inside memory. Even though it has been explored for more than 50 years, technology challenges prevented the successful materialization of processing in memory in commercial systems. UPMEM is a French startup that has designed, fabricated, and commercializes the first publicly available real-world processing in memory architecture. The UPMEM architecture consists of DDR4 chips that embed small cores called DRAM processing units or DPUs. Our work is an introduction to the UPMEM PrIM architecture and programming model. It's a characterization of the architecture of the DPU, and it's a benchmarking and workload suitability study. Our main contributions are a comprehensive characterization and analysis of the first commercially available processing in memory architecture, and PrIM, the first benchmark suite for a real-world processing in memory architecture. PrIM contains 16 workloads that are memory-bound in conventional processor-centric systems. We characterize PrIM benchmarks using strong and weak scaling experiments and compare them to their CPU and GPU counterparts. Main takeaways of our work are workload characteristics for processing in memory suitability, programming recommendations, suggestions and hints for hardware and architecture designers of future PIN systems, and PrIM, which can serve as programming samples and for the evaluation and comparison of current and future PIN systems. Data movement in current computing systems dominates performance and energy consumption. According to recent studies, data movement accounts for 62% of the total system energy in consumer applications, 40% in scientific applications, and 35% in mobile applications. If we take a look at the current system on chip, we will find CPU cores, GPU cores, cache hierarchy, accelerators, and among all these components and the main memory, there is a lot of data movement. One way to deal with this data movement bottleneck is to turn compute systems into something more data-centric. And processing in memory is a way of doing this. Processing in memory proposes computing where it makes sense or where the data resides. UPMEM has fabricated the first processing in memory real-world architecture. The UPMEM architecture consists of DDR4 DIMMs that contain PIN chips. Inside each PIN chip, we find memory arrays and DPUs, some small in-order processors. Our work introduces the UPMEM PIM architecture, and it's a benchmarking and experimental characterization of this architecture. Throughout our paper, and also throughout this presentation, you will find some color boxes with general programming recommendations, programming recommendations derived from our analysis, key observations, and key takeaways. The color, format, and numbering of these boxes is the same in the paper and throughout the presentation to ease the connection between them. All our codes, microbenchmarks, benchmarks, and scripts are available in our public repository. Let's take a look at the outline of this presentation. First, we are going to give an overview of the UPMEM-based PIN system. Next, we will introduce some important concepts in processing in memory programming and about the interaction between the CPU and the DPUs. Then we will talk about the DPUs, the DRAM processing units, and we'll characterize their arithmetic throughput and bandwidth. Next, we will introduce our benchmarks, and we will explain why we have chosen these benchmarks. Then we evaluate these benchmarks with the strong and weak scaling experiments and compare them to CPU and GPU. And finally, we provide some key takeaways. Let's start with the overview of the UPMEM-based PIN system. UPMEM DIMMs coexist with conventional DIMMs in UPMEM-based PIN systems. The way to integrate these UPMEM DIMMs in the system follows the accelerator model. In the accelerator model, the UPMEM DIMMs can be seen as coprocessors or loosely coupled accelerators. This means that it's necessary to explicitly move data between the main processor or host CPU and the accelerator, the UPMEM DIMMs. And it's also necessary to explicitly launch the kernel that is going to run in the UPMEM processors or DPUs. This model resembles GPU computing. Let's take a closer look at the system organization. We will typically find a host CPU, some DIMMs that DRAM DIMMs that represent the main memory, and some UPMEM DIMMs that represent the PIM-enabled memory. These UPMEM DIMMs typically contain 8 or 16 chips. Every 8 chips are one rank. So in UPMEM DIMMs, we will find 1 or 2 ranks. Inside each PIM chip, there are 8 DRAM banks of size 64 megabytes that are called main RAM or MRAM banks, and 8 DRAM processing units or DPUs. In total, there are 64 DPUs in a rank. If we take a quick look at the DPU, we will see the in-order pipeline and 2 SRAM-based memories, 1 for instruction and 1 for operands. Then we also find a DMA engine to access the MRAM bank. In our work, we have used an UPMEM-based PIM system with 20 UPMEM DIMMs of 16 chips each, in total 40 ranks. This system contains up to 2,560 DPUs and 160 gigabytes of PIM-enabled memory. In this picture, we can identify the 2 CPUs that are part of this UPMEM-based PIM system, some DRAM DIMMs, and some UPMEM DIMMs of PIM-enabled memory. In our study, we have also used a smaller system with 640 DPUs and 40 gigabytes of PIM-enabled memory. Now let's talk about UPMEM PIM programming. We start with our first programming example, vector addition, which is one of the benchmarks in PrIM. In vector addition, we typically have 2 arrays, A and B, and we perform the element-wise addition of these 2 arrays. We add 2 elements of A and B and store the results in an output array C. So the way to program this in the UPMEM-based PIM system is by equally partition the input and the output array across DPUs, such that one chunk of the arrays is assigned to DPU 0, DPU 1, 2, 3, and so on. And inside each of the DPUs, we use tasklets or software threads that run on the DPU to process the data that has been assigned to each DPU. In this case, tasklet 0, tasklet 1, and is the same in the rest of DPUs. When it comes to implementing these workloads in the UPMEM-based PIM system, it's important to take into account some general programming recommendations that we have gathered from UPMEM documents. The first of these general programming recommendations is to execute on the DPUs portions of parallel code that are as long as possible. This is a good recommendation for 2 reasons. First, because this allows us to maximize the usage of the DPUs. And second, because this will allow us to amortize the overhead of explicit data movement between the main memory and the PIM-enabled memory. The second programming recommendation is split the workload into independent data blocks, which the DPUs operate on independently. This is a very important recommendation because, as we will see, there is no direct communication channel across DPUs. So if one DPU needs to access data that resides in the MRAM bank of another DPU, the access will have to be done over the host CPU. And this is quite costly, as we will see. Another recommendation is to use as many working DPUs in the system as possible. This makes sense to exploit all available parallelism. And finally, launch at least 11 tasklets per DPU. We will see why soon. Let's try to understand more about these, the data transfers that are needed between the CPU and the DPUs. So typically, we will have data movement between main memory and the PIM-enabled memory. These are what we call the CPU-DPU data transfers, and also between the PIM-enabled memory and the main memory. These are what we call the DPU-CPU data transfers. There are 3 types of data transfers. First, serial CPU-DPU and DPU-CPU transfers. In these data transfers, we are targeting a single DPU or a single MRAM bank. This means that if we launch multiple transfers to multiple MRAM banks, serial transfers, they will execute sequentially or serially, one after the other. In that sense, the parallel CPU-DPU and DPU-CPU transfers can be more efficient and they can provide more bandwidth because they are parallel. This means that we target multiple DPUs at the same time. We transfer buffers or parts of a buffer to multiple DPUs or multiple MRAM banks. And the third type are the broadcast CPU-DPU transfers, where we transfer a single buffer to multiple DPUs. It is possible to have different types of transfers in a program, even though having parallel or broadcast transfers is typically more efficient, as we will see. But in some cases, it's necessary to use serial transfers. This is something that we can see in Select, one of our benchmarks. In Select, we have an input array that we distribute equally across the existing DPUs. And because these chunks that are assigned to each DPU are of the same size, we can use parallel transfers. However, the output is dependent on the values of the input. And for example, in this Select benchmark, what we are doing is removing even values. So if you look at the array, you will see that there are only two odd values in the chunk assigned to DPU 0, two values in the chunk assigned to DPU 1, and one value in the chunk assigned to DPU 2. This means because these transfers, return transfer or output transfers are not going to be of the same size, we'll have to use serial transfers. It's also important to talk about how to perform inter-DPU communication, because there is no direct communication channel between DPUs. This means that inter-DPU communication needs to take place over the host CPU using CPU-DPU and DPU-CPU transfers. In our benchmark suite, you will find example communication patterns. For example, merging of partial results to obtain the final result, which only require DPU to CPU transfers. An example of this is histogram calculation, one of our benchmarks, where the different DPUs create subhistograms that need to be later merged or reduced in the host. In this case, we only need to use DPU to CPU transfer to move these subhistograms to the host CPU. There is other pattern that is the redistribution of intermediate results for further computation. For example, in BFS, another of our benchmarks, every DPU generates a partial output frontier. The CPU needs to gather these partial frontiers, merge or reducing them, and then redistribute the new frontier to the DPUs for a later iteration. This pattern requires CPU to DPU and DPU to CPU transfers. So it's more complex and it's going to be more costly, as we will see. How fast are these CPU, DPU, and DPU, CPU transfers? To measure that, we create microbenchmarks. And we run two experiments. In the first experiment, we target a single DPU and we change the transfer size from 8 bytes to 32 megabytes. In the second experiment, we target one whole RAM, we transfer an array of 32 megabytes, and we change the number of MRAM banks from 1 to 64, which is the maximum inside the same RAM. We do not show in the paper or this presentation experiment with more than one rank because preliminary experiments showed that the current UPMEM SDK parallelizes transfers only within the same rank. One important thing to take into account upfront is that the maximum transfer bandwidth is going to be limited by the DDR4 bandwidth because all this communication happens over the memory bus. And this connects us to one of our general programming recommendations. Try to run pieces of code that are as long as possible on the DPUs, because this is the way to amortize the overhead of the data transfers. Now let's take a look at the results on one DPU. As I said, we vary the transfer size from 8 bytes to 32 megabytes. The y-axis represents the sustained CPU, DPU, and DPU, CPU bandwidth. These are the results for CPU to DPU transfers, and these are the results for DPU to CPU transfers. As we can see, in the beginning, the latency, the bandwidth increases with the transfer size, and at some point it starts saturating. One key observation, which is key observation number 7 in our paper, is that larger CPU-DPU and DPU-CPU transfers between the host main memory and the MRAM of the DPUs result in higher sustained bandwidth. Now let's take a look at the results for one rank. In this case, we run serial, parallel, and broadcast CPU-DPU transfers and serial and parallel DPU-CPU transfers. The number of DPUs varies between 1 and 64, as we can see in the x-axis. These are the results for the serial transfers, which are the bandwidth is completely flat because the transfers are executed serially to different DPUs, and these are the results for the parallel transfers and broadcast transfers. Key observation is that the sustained bandwidth of parallel CPU-DPU and DPU-CPU transfers between the host main memory and the MRAM banks of the DPUs increases with the number of DPUs inside the rank. More analysis and observations about these experiments can be found in our paper. Now, let's talk about the architecture of the DRAM processing unit and let's analyze its performance. So recall that in a typical UPMEM-based PIM system, we have a host CPU, we have some DRAM DIMMs that are the main memory, and we have some UPMEM DIMMs that are the PIM-enabled memory. Inside each of these PIM chips, we have a DDR4 interface for the host CPU to access the MRAM banks. We have a control and status interface for the host CPU to send commands to the DPU. We have 8 of these MRAM banks of size 64 megabytes, a DMA engine to access them, 2 SRAM-based memories. One is an IRAM instruction memory of size 24 kilobytes that can hold up to 4,096 instructions, and the WRAM or working RAM of 64 kilobytes, which is a scratchpad that can store input and output operands. And then we have the in-order pipeline. Let's take a closer look at the pipeline. This is an in-order pipeline that in current generations can run at a frequency of up to 350 megahertz. This is a fine-grained multi-threaded architecture that has 24 hardware threads. Each of these hardware threads has its own architectural context, including a program counter. And there are 14 pipeline stages. The first of the stages, dispatch, is the thread selection. Then we have stages for instruction fetch, for access to the register file, formatting the input operands, and ALU stages, where we can execute arithmetic and logic instructions or access the WRAM. And finally, result formatting stages. We're going to analyze what's the arithmetic throughput that we can achieve in the DPU. To this end, we measure the maximum arithmetic throughput for different data types and operations using a microbenchmark where we stream over an array in WRAM and perform read, modify, write operations on every element of this array. We run the experiments on one DPU and vary the number of tasklets from 1 to 24. We run experiments for arithmetic operations like addition, subtraction, multiplication, and division, and for different data types, 32 and 64-bit integer operands and floating point operands of single and double precision. We measure cycles with the accurate cycle counters that the SDK provides. And in our measurements, we include the accesses to WRAM, including the address calculation, because there is where the operands are stored. Let's take a very quick look at one of our microbenchmarks. This is the addition for 32-bit integers. At the top, you can see the high-level language code. At the bottom, the compiled code in UPMEM ISA. This for loop compiles to these instructions. This is the access to WRAM. Here we can see the address calculation instruction and the load instruction. Next, we find an addition, and finally, the store to WRAM instruction. Let's take a look at the results. So these are the results for integer 32, 64, floating point operands, and double operands. The y-axis represents the arithmetic throughput in mega operations per second, and the x-axis the number of tasklets. These are the results for addition and subtraction. These are results for multiplication and division, and these are the results for the rest of data types. Key observation number one in our paper is that the arithmetic throughput of a DRAM processing unit saturates at 11 or more tasklets. This observation is consistent for different data types and operations. And what we are doing here is showing why the fourth general programming recommendation that we explained before. Another important observation is that the arithmetic throughput of addition and subtraction of 32-bit integers is 17% faster than the arithmetic throughput of 464-bit integers. Can we explain this peak throughput? Yes, we can explain it if we consider that the peak throughput is reached at 11 or more tasklets, and when the pipeline is full, one instruction retires every cycle. We can obtain the maximum theoretical arithmetic throughput with this expression that where the arithmetic throughput in operation per second equals the frequency of the DPU divided by the number of instructions to perform one operation. We can obtain this number of instructions if we inspect the code of our microbenchmarks. On the left-hand side, we can see the high-level language code for 32-bit and 64 bits. On the right-hand side, we can see the compiled code. These 6 instructions correspond to the inner loop of the addition microbenchmark for 32-bit integers, and these instructions for 64-bit integers. If we compare both, we see that the only difference is this add C. The reason is that the ELUs in the DPU pipeline are of 32 bits. So if we are operating on 64-bit integers, we first need to operate on the lower 32 bits and then on the higher 32 bits. That's the reason for this add C. And this is why we have 6 instructions in the 32-bit microbenchmark and 7 instructions in the 64-bit microbenchmark. So if we use these number instructions in this expression, we will obtain that the theoretical arithmetic throughput for 32-bit addition and subtraction is 58.33, and for 64-bit is 50 mega operations per second, which is very similar to what we are measuring in our experiments. Another important observation is that there is a huge throughput difference between addition and subtraction and multiplication and division. The main reason is that the DPUs don't have a 32-bit multiplier, and multiplication and division are implemented based on an instruction that performs bit shifting and addition in one cycle. This means that a multiplication or division can take up to 32 of these instructions. Another important observation is that there is a huge throughput difference between integers and floating point operands. Key observation number 2 explain this. First, we see that the DPUs provide native support for 32 and 64-bit integer addition and subtraction, which leads to high throughput for these operations. But DPUs don't natively support 32-bit or 64-bit integer multiplication and division, as we have seen in the previous slide, or floating point operations. These operations are emulated by the UPMEM runtime library, leading to much lower throughput. Now let's take a look at the WRAM and the interaction between the pipeline and the WRAM memory. We have a microbenchmark to measure the bandwidth for the stream benchmark. We implement the 4 versions of a stream benchmark: copy, add, scale, and triad. The operations performed in add, scale, and triad are respectively addition, multiplication, and addition plus multiplication. In our experiments, we vary the number of tasklets from 1 to 16, and we show results for 1 DPU. We don't include accesses to MRAM because we just want to measure the access to WRAM. Let's take a very quick look at the codes of the stream benchmark. This is the copy benchmark, this is the add benchmark, scale, and triad. In each of the iterations of these inner loops, we access, in the case of copy, we read 8 bytes from WRAM and write 8 bytes, and there are no arithmetic operations. In the add benchmarks, we read 16 bytes and write 8 bytes, and there is one addition. In the scale benchmark, we read 8 bytes and write 8 bytes, and there is one multiplication. And in triad, we read 16 bytes, write 8 bytes, and perform one multiplication and one addition. Let's take a look at the results. In the plot, we see the sustained WRAM bandwidth on the y-axis and the number of tasklets on the x-axis. These are the results for copy, these for add, and these is scale and triad. Can we estimate this bandwidth? If we assume that the pipeline is full and bytes is the number of bytes that we read or write from WRAM, the theoretical WRAM bandwidth in bytes per second can be expressed as the number of bytes times the frequency of the DPU divided the number of instructions. For example, for copy, we just need 2 instructions, one WRAM load and one WRAM store. If we are using 11 tasklets or more and the pipeline is full, we will need 22 cycles to execute these 2 instructions. So in 22 cycles, we are reading or writing 11 times 16 bytes. And this gives us a WRAM bandwidth of 2,800 megabytes per second, which is essentially the same than what we have measured. For add and the other scale and triad, we can obtain similar values of the theoretical maximum and compare them to the measured values as we do in our paper. You can find more analysis about the WRAM bandwidth for different access patterns in our paper. Now, let's measure what's the latency and bandwidth of MRAM. To do that, so our goal is to measure the MRAM bandwidth for different access patterns, and we use several microbenchmarks here. First, we use a microbenchmark which measures the latency of a single DMA transfer. We have 2 instructions, MRAM read and MRAM write, to move data from MRAM to WRAM and from WRAM to MRAM. The size of these transfers is a parameter of these 2 instructions. We also use the stream benchmark. We create 2 benchmarks for a strided access pattern, and we also implement the gaps benchmark for random access pattern. In this analysis, we do include the accesses to MRAM. Let's start with the latency of a single DMA transfer. In these plots, we can see the bandwidth on the left y-axis, latency on the right y-axis, and data transfer size in the x-axis. We can calculate the bandwidth after measuring the MRAM latency. The MRAM bandwidth is the size of the transfer multiplied by the frequency of the DPU divided by the MRAM latency, which is the value that we are measuring. But we can also model this MRAM latency with a linear expression. The MRAM latency in cycles is equal to a fixed cost, alpha, plus a variable cost, beta times size. We can see how this model matches perfectly our measurements. In our measurements, we obtain that beta is equal to 0.5 cycles per byte. This means that we can read 2 bytes in 1 cycle. The theoretical maximum MRAM bandwidth this way is 700 megabytes per second at 350 megahertz. And the bandwidth that we are obtaining in our measurements is very close to these 700 megabytes per second, as we can see. So important key observation here is that the access latency of the MRAM increases linearly with the transfer size, and that the maximum theoretical MRAM bandwidth is 2 bytes per cycle. Another interesting observation is that read and write accesses to MRAM are symmetric. The sustained MRAM bandwidth increases with the data transfer size. This way, one programming recommendation is for data movement between the MRAM bank and the WRAM, use large DMA transfer sizes when all the access data is going to be used, because this way we can enjoy higher bandwidth. We can find more programming recommendations and key observations in our paper. Now let's take a look at the results for the stream benchmark. We use exactly the same codes as we did for MRAM, but now we include the accesses to MRAM and the read accesses to MRAM and the write accesses to MRAM. We have another version of the copy DMA benchmark where we don't stream over the array that we have in WRAM. We simply move a chunk from MRAM to WRAM and then write back this chunk to MRAM with these two instructions. Let's take a look at the results. These are the results for copy DMA. We can see that the sustained bandwidth of copy DMA is very close to the theoretical maximum of 700 megabytes per second that we obtained before. This means that we can achieve a total bandwidth of about 1.6 terabytes per second for a full UPMEM-based system with 2,556 DPUs, which is significantly higher than the maximum bandwidth in the most powerful GPUs these days. Another observation is that copy DMA saturates with 2 tasklets, even though the DMA engine can only perform 1 transfer at a time. The reason for this is that using 2 or more tasklets guarantees that there is always a DMA request in queue to keep the DMA engine busy. And this is why we achieve a little bit higher bandwidth when we use 2 or more tasklets. These are the results for add and copy, and these are the results for scale and triad. We observe that copy and add saturate respectively at 4 and 6 tasklets, while scale and triad saturate at 11 tasklets. The reason for that is that in copy and add, the latency of MRAM accesses becomes longer than the pipeline latency after 4 and 6 tasklets respectively. So the latency of the MRAM accesses dominates in these 2 benchmarks. While in scale and triad, the pipeline latency is always longer than the MRAM latency for any number of tasklets. And the reason is that these 2 benchmarks use the costly multiplication. So key observation number 5, when the access latency to an MRAM bank for a streaming benchmark like copy DMA, or add is larger than the pipeline latency, the performance of the DPU saturates at a number of tasklets smaller than 11. We are talking about memory-bound workloads. However, when the pipeline latency for a streaming benchmark like scale or triad is larger than the MRAM access latency, the performance of the DPU saturates at 11 tasklets. This is what we call a compute-bound workload. We will talk soon again about memory-bound and compute-bound workloads. But first, let's take a look at the strided and random access patterns. For the strided access pattern, we prepare 2 microbenchmarks. The first microbenchmark is coarse-grained strided access. We call it coarse-grained DMA approach. In this microbenchmark, what we are doing is moving whole chunks from MRAM to WRAM and performing the strided accesses in WRAM, as we can see in this code. When we are done, we write back the chunks to MRAM. In the fine-grained strided access and also in random access, we only access from MRAM those elements that really need to be accessed. So that's why we have this external loop where we stride over some array in MRAM, and we only read from MRAM one particular element, in this case of size 64 bits. And then we write the element in the corresponding output position. So let's analyze the performance of these 2 versions. Here, we can see the sustained MRAM bandwidth versus the stride. And on the figure of the right, we also have in the last column the results for the random access pattern. So first observation is that there is a large difference in maximum sustained bandwidth between the coarse-grained and the fine-grained DMA approaches. The reason is that the coarse-grained DMA approach is moving large chunks of size 1024 bytes between MRAM and WRAM or vice versa, while the fine-grained DMA approach uses only 8-byte transfers, which have much lower bandwidth. The random access microbenchmark achieves very similar maximum sustained bandwidth to the fine-grained stratified approach because it's also using a fine-grained DMA approach. Another observation is that the sustained MRAM bandwidth of coarse-grained DMA decreases as the stride increases. And the reason is that the effective utilization of the chunk of data that we are moving becomes smaller as the stride becomes larger. So for example, if the stride is 4, we are only using 1/4 of the transfer data. So the effective bandwidth is only 1/4 of the total bandwidth. And this is what makes that at some point, the fine-grained strided approach starts to be more efficient than the coarse-grained strided approach. For 16 or larger stride, the fine-grained DMA approach achieves higher bandwidth. And the reason is that 1/16 of the maximum sustained bandwidth is smaller than these 72.58 megabytes per second that we can achieve with the fine-grained strided approach. So programming recommendation 4 for strided access patterns with a stride smaller than 16 8-byte elements, fetch a large contiguous chunk and access then this chunk in WRAM. While for larger strides and random access patterns, fetch only the data elements that are needed from the MRAM bank. Now let's take a closer look at the interaction between the arithmetic throughput in the pipeline and the access to MRAM. To do that, we create a microbenchmark that allows us to characterize memory-bound regions and compute-bound regions for different data types and operations. The microbenchmark loads one chunk from MRAM into WRAM, performs a variable number of operations on the data in WRAM, and then writes back to MRAM. This experiment is inspired by the Roofline model, where we represent the performance versus the arithmetic or operational intensity. We define the operational intensity as the number of arithmetic operations performed per byte accessed from MRAM, and it's expressed in operations per byte. One important thing to take into account is that the pipeline latency in these experiments changes with the operational intensity, but the MRAM access latency is fixed. This is very briefly the microbenchmark that we have used. We load data from MRAM to WRAM, then we perform a number of repetitions where we execute some arithmetic operation like addition, subtraction, multiplication, or division, and then we write back to MRAM. We have an input parameter, which is input repeat. If this input repeat is greater or equal to 1, this tells us the number of repetitions of the arithmetic operation per input element. If input repeat is smaller than 1, this means that we are only accessing some of the elements in the chunk that we are moving to WRAM. And these are the results for 2 data types, 32-bit integer and floating-point operands, and 2 arithmetic operations, addition and multiplication. We will analyze these results now, but first of all, we have to say that we have observed very similar trends for other data types and operations as well. So let's take a look at the results for addition of 32-bit integers. In this case, here we are representing with a logarithmic scale the arithmetic throughput, the mega operations per second, and the operational intensity in the x-axis. We start from very, very low operational intensity, 1/2048, which essentially means 1 addition every 8K 32-bit integers. And this is the throughput that we can achieve for a single tasklet. And this is the throughput for 2 tasklets. And what we can see is that for this very, very low operational intensity, the maximum arithmetic throughput is obtained with 2 tasklets. So with 16 tasklets, the throughput is exactly the same as for 2 tasklets, which makes sense because we have very, very little amount of computation here. And this is almost essentially the same as the copy DMA stream benchmark that we showed before, where we had the saturation point at only 2 tasklets. So, and this is the trend for also higher operational intensities. At some point, the throughput starts saturating with 3 tasklets, and this throughput remains the same for higher number of tasklets, and also for higher operational intensities. And at some point, we find that the throughput starts saturating at 11 tasklets. And after that, the throughput remains flat for higher operational intensities. So here we can distinguish between the memory bound region, where the arithmetic throughput increases with the operational intensity, and the compute bound region, where the arithmetic throughput is flat at its maximum. And the operational intensity that represents the transition between the memory bound and the compute bound region is what we call the throughput saturation point. This throughput saturation point is very low for addition of 32-bit integers, as low as 1/4, but it's even lower for other data types and operations. So key observation number 6 is that the arithmetic throughput of a DRAM processing unit saturates at low or very low operational intensity. And this means that DPUs are fundamentally compute-bound processors. We expect that most real-world workloads will be compute-bound in the UPMEM architecture because of this reason. Now let's talk about PrIM benchmarks. Our goal is to come up with a common set of workloads that can be used to evaluate the UPMEM processing in memory architecture, compare software improvements and compilers, and compare future PrIM architectures and hardware, among other purposes. We have 2 key selection criteria. We select workloads from different application domains, and we also select workloads that are memory-bound on processor-centric architectures. In total, we have 14 different workloads and 16 benchmarks, because for 2 of the workloads, we have 2 benchmark versions. This is the list of applications domains. We have benchmarks from dense and linear algebra, dense and sparse linear algebra, databases, data analytics, graph processing, neural networks, bioinformatics, image processing, 2 benchmarks for image histogram, and parallel primitives like reduction, prefixsum, and matrix transposition. We can obtain the Roofline model for these workloads on a real CPU, an Intel Xeon CPU, and we observe that all these workloads fall in the memory bound area of the Roofline. We can show that these benchmarks are diverse in terms of memory access pattern with sequential, strided, and random access patterns, and also in terms of computation pattern, because they use different operations and data types. Synchronization and communication, we have some of them using intra-DPU synchronization primitives like handshakes, barriers, and mutexes, and also some of the benchmarks use inter-DPU synchronization. In particular, we find 2 main patterns of inter-DPU synchronization, as we mentioned before. Some of them for result merging, some others for redistribution of intermediate results. Now let's evaluate these workloads on 2 UPMEM PIM-based systems and compare their performance to CPU and GPU. So we evaluate the processing in memory benchmarks on 2 UPMEM-based PIM systems with 2,556 DPUs and with 640 DPUs. We perform strong and weak scaling experiments. Recall that strong scaling refers to the execution time of a program when we change the number of processors for a fixed problem size. Weak scaling refers to the execution time of a program when we increase the number of processors, but we have a fixed problem size per processor. We run experiments for strong scaling on 1 DPU, changing the number of tasklets on 1 rank and on up to 32 ranks. And for weak scaling, we run experiments on 1 rank. We also compare to CPU and GPU, and in particular, we use an Intel Xeon CPU and an NVIDIA Titan V GPU. And here, and in our paper, you can find the data sets that we have used for strong scaling, weak scaling, and also the MRAM WRAM transfer sizes that we have used in our experiments. The PrIM benchmarks repository includes all data sets and scripts that we have used in our evaluation. Let's take a look at the strong scaling results on one DPU. So here we have the results for the 16 benchmarks. We set a number of tasklets to 1, 2, 4, 8, and 16, as we can see in the x-axis here. And we show the breakdown of execution time with the DPU kernel time, the inter-DPU communication time for those kernels that need it, the CPU-DPU transfer time, and the DPU-CPU transfer time, and finally, the speed up of the DPU kernel time over one tasklet. So let's take a look at some observations. First of all, is that for most of these benchmarks, the best performing number of tasklets is 16. And actually, we can see that the speed up is something between 1.5 and 2 when we double the number of tasklets from 1 to 8. And then the speed up is something between 1.2 and 1.5 when we double from 8 to 16. The reason is that the pipeline throughput saturates at 11 tasklets, as we already know. So this means that a number of tasklets greater than 11 is typically a good choice for most real-world workloads. Actually, in 16 out of 19 kernels in 16 benchmarks, this is the case. We can also see that some of these benchmarks, in particular these 7, don't use intra-DPU synchronization primitives. In some others, there is intra-DPU synchronization, but this is very lightweight. However, in 3 of these kernels, they use mutexes, and this causes contention when accessing shared data structures. For example, in one of the versions of histogram, we have a single histogram that is being updated, but we have a single histogram per DPU, which is updated by all the tasklets running on the DPU. This makes that the best performing number of tasklets is not 16, but 8. And the reason is that we have much more contention in the mutex when we have 16 tasklets trying to update this shared histogram. So one key observation is that the intensive use of intra-DPU synchronization across tasklets using mutexes, barriers, or handshakes may limit the scalability, which makes that sometimes the best performing number of tasklets is lower than 11. We find also other cases which are like the exception. For example, the add kernel in scan SSA saturates at a number of tasklets that is lower than 11. And the reason is that this is not a compute intensive kernel. Essentially, in the add kernel, what we are doing is going over one array and adding a single value. This resembles the stream add benchmark, where we saw that the saturation point was lower than 11. BS is another benchmark that shows similar behavior. So one key observation is that most real-world workloads are in the compute bound region, and are very few exceptions like scan SSA, the add kernel, and BS. You can find more analysis, more key observations, and programming recommendations in our paper. Let's also take a very quick look at the strong scaling results for one rank. Here we can see the results for the 16 benchmarks. We set the number of tasklets to the best performing one in the previous experiments, and now we change the number of DPUs from 1 to 64. The experimental results show the breakdown of the execution time on the DPU, the inter-DPU synchronization time, the data transfers time between CPU and DPU, and between DPU and CPU, and finally, the speed up of the DPU kernel execution over one DPU. So some observations is that most of these benchmarks scale linearly with the number of DPUs. And scaling is only sublinear in two of them, BFS and NW. In BFS, the reason is that there is load imbalance because it's a graph algorithm and graphs are typically have an irregular topology. So different DPUs finish at different times. And in NW, what happens is that we are processing diagonals in a two-dimensional matrix. So for the shorter diagonals, we don't use more DPUs, even though there might be more DPUs available in the system. So this is why it scales sublinearly. Another observation is that these 6 benchmarks don't need inter-DPU synchronization. While inter-DPU synchronization is relatively lightweight for some of the other benchmarks, where we see that 64 is the best performing number of DPUs. However, three other benchmarks, BFS, MLP, and NW, require heavy inter-DPU synchronization that may limit the scalability of these benchmarks. You can find more key observations and programming recommendations in the paper, as well as you can also find in the paper the complete results for the strong scaling experiments on 32 ranks and the weak scaling experiments on 1 rank. Now let's take a quick look at the evaluation and comparison to CPU and GPU. As I said, we compare to one state-of-the-art CPU and one state-of-the-art GPU. The CPU and GPU versions of the PrIM benchmarks are also available in our repository. In these experiments, we use the largest data set that we can fit in the GPU memory, and for the execution time on the UPMEM-based PIN systems, we are considering the DPU kernel time and the cost of inter-DPU communication. These are the results. This is the speed up in logarithmic scale over the CPU, and here we have the different benchmarks and some geomean values. These are the results for those workloads that we find more pin suitable, as we will see. These are the results for those workloads that are less pin suitable, and these are the values of the geomean for the two types of workloads and the overall geomean. So one observation here is that the two UPMEM-based PIM systems that we are evaluating outperform the CPU for all benchmarks except SPMB, BFS, and NW. And the speed up that they obtain is respectively 93 times and 27.9 times for 13 of the PrIM benchmarks. If we compare to the GPU, we see that the larger UPMEM-based PIN system outperforms the GPU for 10 of the 16 PrIM benchmarks with an average of 2.54 times. And even for the smaller UPMEM-based PIN system with 640 DPUs, these are the most suitable workloads. And we achieve in this UPMEM-based PIN system a performance that is within 65% the performance of the GPU. So key observation number 19 relates to the key characteristics of these workloads that are more pin suitable and perform in the larger system faster than on the GPU. The three key characteristics are streaming memory accesses, no or little inter-DPU synchronization, no or little use of integer multiplication, integer division, or floating point operations. So these three characteristics make a workload potentially suitable to the UPMEM PIM architecture. We can also take a very quick look at the energy comparison, and we see that the 640 DPU system consumes on average 1.64 less energy than the CPU for all 16 PrIM benchmarks. And actually for 12 of the PrIM benchmarks, the 640 DPU system provides energy savings of 5.23 times over the CPU. You can find more analysis related to this energy comparison in our paper. We finalize with some key takeaways to summarize our findings. So recall that we found that there is a memory bound region and a compute bound region, and they are typically separated by a throughput saturation point that is very, very low in the current UPMEM-based PIN systems. So key takeaway number one is that the UPMEM PIM architecture is fundamentally compute bound. And as a result, we expect that the most suitable workloads are those that are highly memory bound in conventional architectures. Or key takeaway number two is that the most well-suited workloads for the UPMEM PIM architecture use no arithmetic operations or use only simple operations. For example, bitwise operations or integer addition and subtraction. And key takeaway number three is that the most well-suited workloads for the UPMEM PIM architecture require little or no synchronization across DPUs, what we call the Inter-DPU synchronization. Or key takeaway number four says that the UPMEM-based PIM systems outperform state-of-the-art CPUs in terms of performance and energy efficiency on most PrIM benchmarks. And compared to GPUs, we see that the UPMEM-based systems can outperform GPUs on a majority of PrIM benchmarks, and actually the outlook is even more positive for future PIM systems. We can also say that the UPMEM-based PIM systems are more energy efficient than the state-of-the-art CPUs and GPUs on those workloads where they provide performance improvements. And the reason is that the performance improvements as well as the energy savings that the UPMEM-based PIM systems can provide are due to a huge reduction in the data movement between memory and the processing elements. So we can finalize this presentation with, again, our executive summary. Recall that data movement is a major contributor to execution time and energy consumption in current computing systems. Processing in memory is a paradigm that can alleviate this bottleneck. And even though it has not been materialized over all the time that it has been explored, there is a company, UPMEM, that is fabricating and commercializing real-world processing in memory architectures containing DDR4 chips with small processors called DPUs. In our work, we introduced the PIM architecture and UPMEM programming model. We characterize the architecture of the DPU. We perform a benchmarking and workload suitability study and provide some key contributions like a comprehensive characterization and analysis of this UPMEM-based PIM system and a benchmark suite, PrIM, that contains 16 workloads that are memory bound in conventional processor-centric systems. We evaluate these workloads with a strong and weak scaling analysis and compare their performance to CPU and GPU. Our main takeaways are the workload characteristics for PIM suitability, as we have discussed, programming recommendations, suggestions, and hints for hardware and architecture designers of future PIM systems, and the PrIM benchmark suite that can be used as programming samples and also for evaluation and comparison of current and future PIM systems. As I said before, all our codes are publicly available in our repository. Thank you very much for your attention.